This second video on electrophilic addition will look at one small modification. We're going to be considering the hydration of an alkene. Things will be pretty similar as the first video, so we're going to be looking at an alkene reacting with an acid, HBr. The change is, in this case, the use of water as a solvent. We get a different product with similar regioselectivity. In this case, it's the alcohol that is added on the most substituted position. The first part of the mechanism is pretty similar as what we saw previously. That is the addition of the proton on the alkene shown with the electrons from the alkene attacking the proton, forming two possible intermediate, the same one that were shown before, with the tertiary carbocation a lot more stable than the primary carbocation, meaning that this primary carbocation is formed as a minor intermediate, and therefore we can just continue after with the most stable tertiary carbocation. Now that's where things start to be a little different. So we get now two possibilities. We have, after the first step, still the bromide that is formed as a leftover of the hydrobromic acid, but we also have the water molecule. So we have two possible nucleophiles that can attack on the carbocation. The bromide can attack. That can be shown like the previous example, forming reversibly the final product, or a possible final product, that would be what we saw on the video number 1 on electrophilic addition 1, that is the 2-bromo 2-methyl propane. If the water, though, attacks on the tertiary carbocation, we're going to, of course, get a different different intermediate, not carbocation. So that would be looking like this. So now, which of these two intermediates form a larger amount? There are two variables to consider here. First, which of the two nucleophiles is the most nucleophilic? That will favor the bromide with a negative charge. The water being neutral, the oxygen being neutral, is less nucleophilic than the bromide. So that would seem to favor the bromide as a nucleophile adding on the carbocation. But in this case, the most important variable is the fact that water here, being underneath the arrow, is the solvent. So the concentration of water, being the solvent, is much larger than the concentration of the bromide, being in more dilute condition, because being the reactant. Therefore, we can say that the most important, or the major intermediate, will be this positively charged intermediate, whereas the product form here will be in minor amount. And then we can finish the mechanism with the proton being lost and forming, again reversibly, the 2-methyl 2-propanol. So in this case, we have a reaction following the same regioselectivity as presented in electrophilic addition 1, hydrobromination of an alkene. This product will be formed when the solvent is a non-participating solvent, like THF, like a normal ether, or like a solvent that is not nucleophilic. In presence of a nucleophilic solvent, water is an example, but methanol would be another example. You can find other example too with ammonia or other amine solvent. Then the solvent being in much larger concentration, perhaps less nucleophilic, perhaps as much nucleophilic as the bromide, will influence the outcome of the reaction, and the product form will be the product derived from the addition of the solvent on the most substituted carbocation.